let's talk about where we're going. So we finished the first two parts of the course. Now the first part of the course, which was a while ago, that dealt with techniques of integration. So we said, hey, this integration is kind of fun, but it's a little bit challenging. So how can we get better at it? And sort of the moral of that part of the course is to say, well, there's not much we can actually integrate, so let's learn to rewrite things. And that was pretty much all our tools, was how do we learn to rewrite expressions, which is why there's a lot of algebra and trig involved in that part of the course. The second part of the course, which is what we just finished, is about applications of integration. It's like, now we have this tool, is it good for anything? And the answer is, yeah, it's good for a lot of stuff. Anytime when you're looking for a total of anything, that's an integration problem. And the way that it works is you say, I'm looking for a total of something. I'm going to break my big thing up into little parts, each part of which is easy to figure out. And now I add them all back together. And that's the whole idea of integration. Break things into small parts, figure out each small part, add them back together. Now the third part of the course is going to feel completely different. So where are we going? Well, we're going to start by talking about approximating functions. And this is an idea that we saw in Calc 1, where it says, if I have a function f of x, I can approximate it by its tangent line. So I can say that if I have a function f of x, and I'm looking for x near a, it's approximately f of a plus f prime of a times x minus a. Or I could say, well, it's some number plus some other number times x minus a. Now, the key here is that there's a squiggly line here. Now, the squiggly line indicates that this is not exact, because it's not. It's an approximation. And it's only good near a. And the further you get from a, the worse you get. We might say, okay, maybe can I do a better approximation? Because I'm only doing a line. Can I use a little bit more information? And the answer is, well, yeah, you can do that. So what you can do is you could get and use the second derivative. Because the idea of tangent lines are saying, let's try to find the line which matches both the function and its derivative at that point. So you could say, well, let's match the function, its first derivative, and its second derivative. So that's three things. And it turns out that it's possible to do that if you use a quadratic. Now, we'll go into the details much later on about exactly how, but it's possible. Now, you might say, okay, well, that's better, but why stop at 2? Why not 3 or 4, 5 or 100 or 1,000,000? Why even stop at all? Let's use all the derivatives so that we could say that f of x, well, it's some constant plus some constant times x minus a plus some constant times x minus a squared, and so forth and so forth. And this magical thing happens that in some cases, our squiggly line becomes an equality. Now, it won't happen all the time, but it does happen in many cases which are useful. Now, you might say, okay, well, what's that good for? Well, if you look at what we have, you can look at this and say, it's kind of like a polynomial in that it's a polynomial, just with a lot of terms. Now, why do we care about polynomials? Well, if you think about a computer, what can a computer really do? When you get down to it, what operations can a computer do? It can do addition, which is basically subtraction. And what else can it do? Multiply. And basically that's it. A computer can do those two things. It can add and it can multiply. And not much else. So anything that's a computation, you want to turn it into something that involves just addition and multiplication. Now, what kind of things involve addition and multiplication? And the answer is polynomials. And therefore, that's why we want to do this, because we're going to get to the point where we can take our functions and turn any problem into a problem that involves polynomials, and we can then use polynomials to get our answers, or at least a very good approximation. So that's why we want to do this, because when it comes down to it, when we really want to figure out what's an answer to a computation, we've got to get to a place where we can have tools to answer it. So how are we going to get there? Well, there's going to be 4 stops along the way. So this is where we're going for. And our first stop is we're going to work with ... Now, what does that mean? Well, we're going to talk about what does it mean to have infinitely many terms. Okay, so that's not so bad. That's going to take us about 1 lecture. So the second thing we're going to work with is adding up those things. The plus ... This is probably going to take us 3 weeks. Now, why is it going to take us so long? Well, we're going to talk about what does it mean to add infinitely many things together. And here's the thing. Infinity is really weird. If you don't think infinity is weird now, you might change your mind by the time we're done. And it's not so clear if I'm adding up these infinitely many things, is what I'm adding, does it make sense? And we're going to see that we're going to basically be stuck. There's very few cases where we can actually add up infinitely many things and get the exact answer. We're going to just focus on the question, do we even get an answer at all? And so we call that convergence. Does it converge? Does it diverge? And so that's where we're going to spend a lot of our time in the next couple of weeks. And because we spend so much time there, people are like, I'm losing sight of where we're going. But let's not forget, that's just a step along the way. Remember, we're trying to get up to here. So the next thing is, once we know how to add up a bunch of numbers, we say, well, let's add up and introduce this idea of polynomials. We call these series. And so we're going to add the series together. So now we have these infinite polynomials, and we can talk about, okay, how do they behave? What are their properties? How does calculus interact with this? And once we get past that, we're finally able to get to something which we call Taylor series. And so that's where we're heading. So the idea of Taylor series is, yes, how can I take my function and rewrite it as a series? And then we'll go into applications. We'll see lots of sort of interesting applications. For example, we'll have these functions which look like terrible expressions, and then we're going to say, well, what's the 100th derivative at a point? We could never do that if we did it by hand and took actually 100 derivatives. But this will help us pop the answer out in pretty few short steps. And we'll do other things as well. So there's lots of interesting applications. So that's where we're going. That's our roadmap. All right. So today is the start. Sequences. So here we go. So it's actually pretty short. We're just going to do a little bit of practice. So what is a sequence? A sequence is basically just a list of numbers. And it's indexed. So we represent these by subscripts. So we have the a sub k, meaning this is the kth number. ak plus 1, that's the k plus first number. ak plus 2, that's the k plus second number. And so forth and so on. So it's not just an infinite collection of numbers, it's an infinite collection of numbers that have some order attached to them. So you can say, well, this number is the such and such number on that list. So we can start the index anywhere. We usually start it at 0 or 1, but we can start our initial number anywhere we want. And another way that we'll oftentimes think of these subscripts, or sorry, excuse me, these terms here, is we can think of it as being some function. So if I want to get the nth term in the list, I'm going to call my function of n the nth term in the list. So f of n is a sub n. It gives us a way to describe the pattern. So let's just try some sequences. So we'll write down some terms. So for instance, -1 to the n equals 0 to infinity. So I want to write down the first few terms. What's the first term going to be? Well, that'll be with n equals 0. -1 to the 0 is what? 1. So this is going to give us 1. What's the next term? So it'd be, n equals 0. So what comes after 0? 1. So the next case would be -1 to the 1, which is also known as -1. What's the next term going to be? 1. Because the next term will be So this is the n equals 0, n equals 1, n equals 2. And you probably can guess where we're going. What's next? Negative 1, and so forth and so on. Yeah, so this is going to alternate. Plus 1, minus 1, plus 1, minus 1. Okay, that one's not so bad. How about the next one? So this is 2n. And n goes from 3 to infinity. What's the first term? 6. Because we start at 3. 2 times 3 is 6. So n equals 3. What's the next term going to be? 8. That's the n equals 4. Next term? 10. N equals 5. And then? 12. N equals 6. And so forth. In fact, we can put a little dot, dot, dot. It continues. It continues. All right. How about the next one? 2n plus 6, n equals 0 to infinity. Well, what's the first term? 6. What's the next term? 8. And then 10. And then 12. What do you notice? Yeah, these are the same list. So in some sense, it is possible to describe the same sequence of numbers in multiple ways. And especially what you can do is you can do a shift in the index. So what really happened here is you've really shifted your index down. That corresponds roughly to the same thing as substitution, where substitution says, oh, I'm just changing my name. But really, that just corresponds to shifting here when we talk about sequences. All right. Well, these aren't too bad. We can get through these pretty quickly. 2n from n equals 0 to infinity. What's the first term? 0, and then 2, and then 4. Okay. And you can see where this is going. Yeah. How about, this one's a little bit more challenging. 2n over n squared. N equals 1 to infinity. What's the first term? Well, it'll be 2 to the 1 over 1 to the 2, which is 2. Then what? Yeah, it'll be 2 to the 2 over 2 to the 2, which is 1. All right. And then what's going to happen? It'll be, 2 cubed over 3 squared, which is 8 over 9. So you could write it as 8 over 9. Sometimes, by the way, it does help to leave it as just the form 2 cubed over 3 squared. Now, it looks like it's going down, right? 2, 1, 8 ninths. So what do you think is going to happen in the long run? Ooh, very mysterious. Okay, what's the answer? What's going to happen in the long run? Yeah, be careful. You should never judge something just by what happens at the beginning. Because we're going to be interested not at the start. If we go back to what we talked about on the previous page, the start is not the interesting part. It's the dot, dot, dot. That's where the interesting stuff happens. You should always be a little bit skeptical. And you say, well, it's true that the first million terms look good, but what happens in the first trillion terms? And even then, a mathematician would be, I'm not sure. I'm not sure. So if we check, what is 2 to the 4th over 4 squared? Yeah, we start moving back up again. And then from there, it just gets bigger. So like 32 over 25, and so forth and so on. So yeah, so be a little bit careful. Okay, so that's not so bad. Now, we're going to ask a couple of questions. One question we can ask is, does the sequence converge? So what we have is you have a whole bunch of numbers. And you might say, okay, what's happening on the very end? So you have your first number, your second number, your third number, and you walk all the way, and you say, what's that number way back at the very last one? That number at the end of the list. Well, one of our problems is you can't actually get to infinity. That's a fundamental problem that's going to plague us for a very, very long time. You can't actually get to infinity. It's really impossible. So what are we going to do? Well, we do what we do whenever we have a place where we can't actually get to something. We say, well, let's just get close. So, or as it says here, nearby. Now, what does it mean to get close to infinity? And the answer is, you're close to infinity as you get bigger. Now, that's a little bit imprecise, but what we want to say is we're getting closer to infinity as long as we can talk about what happens for something arbitrarily large. So we can talk about this notion of limits. Limits are, how do I tell about what's happening nearby? So we say that a sequence of a sub n converges to L. So it's getting close to L as n tends to infinity. So that's this notation, limit as n goes to infinity of a sub n equals L. If for any epsilon greater than 0, there is some n which depends on epsilon, so that if n is greater than n sub epsilon, a sub n minus L is less than epsilon. Now, that's a lot of confusing stuff there. Let me just assure you right now, we're not going to test you on this fine a detail. I just want to put it up here. Give you time to think about it over the next couple of weeks as you're enjoying your upcoming break. So, what is this saying? Well, you should think of it as epsilon here. This is a distance. So, in particular, what we want to say when epsilon is greater than 0, it's a really small distance. And our goal here is we want to say, lo and behold, we want to be very close. A sub n and L are very close. That's what's happening here. So the question is, well, how can we guarantee that we're very close? And the way we do it is we say, all right, I need to be close to infinity. So to be close to infinity says, well, I need to be big. So this says n is big, which we think of as close to infinity. So the moral is, as long as I'm closing in on infinity, the distance away from the value that I want, L, is getting small. So that's what's happening. As I get close to one thing, I get close to the other thing. That's what limits are. How can I guarantee I get close? Now, it's possible that things happen. Limits don't always exist. In fact, most limits don't exist. So if there is no such L, we say the sequence doesn't converge, which there's diverges. And again, I already mentioned this before, it's the tail, the end, that's important. So be careful. Watch out. Just because something looks like it's true for the first few terms, don't trust it. Do the math. Work it out. Okay. So, how would we actually prove this using our definition? So, here's a claim. And again, this is just demonstration. So, what happens to 1 over n as n goes from 1 to infinity? Well, let's think about it. What is the sequence 1 over n? What's the first term look like? 1. What's the next term look like? A half. And then? A third. And then? A fourth. And if you kept going, you'd see that these numbers are getting pretty small. So it seems pretty reasonable to think that these should get smaller and smaller and smaller as we keep going. So now how do we prove it? Well, the good news is we can do it pretty simply. So what's our goal? So this is what we want. We want to have 1 over n minus 0 be less than epsilon. So this is my a sub n. This is my L. Because the a sub n is my sequence. The L is my limit. And now I think of, well, if I were going to take the absolute value of 1 over n minus 0, there's another name for that. So that's just 1 over n. The minus 0 doesn't do anything, and n is positive, so if I take the absolute value, that doesn't do anything. So 1 over n, I want that to be less than epsilon. Now, what we'll do is, the question is, what does this say about n? So how can I rewrite this not as 1 over n, but as n? What do I do? So how can I change this 1 over n to an n. Sorry, what?
N to the negative 1.
Well, it's like n to the negative 1, but I don't want n to the negative 1, I want n. So it's like if you have a frown, what do you want to do? You want to turn it upside down, right? Make it a smile. So let's flip it. So that says I want n. Well, if I flip that side, I need to flip the other side, 1 over epsilon. What happens to my inequality? It changes direction. Now, this is what we want. But what do we need? Well, we need to find some n of epsilon so that if n is bigger than that value, then this holds, which is equivalent to saying n is bigger than 1 over epsilon. Well, do you see a candidate? There it is. So the moral is, if you choose your n of epsilon to be 1 over epsilon, then it works. So as you give me an epsilon, say 0.01. And I say, well, how big do you have to be so that you're within 0.01 of 0? Well, what does this say? The rule says, well, if I want to be within 0.01, I should take my epsilon and flip it. If you flip 1 over 0.01, what does that become? It becomes 100, because 0.01 is 1 over 100. So if you flip that, you get 100. So as long as you're over 100, you're close. You're close. All right. All right. Well, okay. That's a little bit technical. We should try something a little bit simpler. Okay. Let's try this one. This is a good question. Let a sub n be 1 plus negative 1 to the n over 2. And let's figure this out. So what is a sub 0? We'll just make a list. What's the first term? It'll be 1, because it's going to be 1 plus 1 over 2. What's the next term? A sub 1. It'll be 0, because it'll be 1 minus 1 over 2. Then the next term? So it's to be 1 plus negative 1 squared, 1 plus 1 over 2, which is 1. Okay, so that's n equals 0, n equals 1, n equals 2. What's the next term going to be? 0. Okay, what's the next one? 1. You might start spotting a pattern here. What's the next one? 0. Okay, what's the next one? 7. No, it's 1 again. It's going to alternate. So this is alternating. So if you think about what's happening, here's your number line, and we say, well, what's happening is that you really have two different things. You have 0 and you have 1. And it's jumping back and forth. 1, 0, 1, 0, 1, 0, 1, 0. And that's what's happening to our terms. Which is a little bit different. If you go back to the previous problem, if you were to draw the number line here, what you would see is that your numbers were doing the following. Here's 0. It was 1, then a half, then a third, then a fourth, then a fifth, then a sixth, a seventh, and eighth. It was doing this. It was moving in. But on the current one, it's not moving into anything. It's hopping back and forth. Okay, so what happens as you head off to infinity? What's the right behavior? What does it get close to? Does it get close to 0? Does it get close to 1? Does it get close to something else? What do you think? Any guesses? 1/2. Ooh, that's a bold guess. I was going to say, there are some people out there who think the answer should be 1/2. And they're also the same people who think that if you take 1 plus 2 plus 3 plus 4 plus 5, and if you add all those up, what should you get? Of course, -1/12, right? There are people out there who believe that. We are not among those people. We are reasonable people. Now, there are reasons to believe that this could make sense, but for us, we don't believe that. So we're going to say, no, that is not -1/12. Okay. By the same logic of that, this pattern of 1, 0, 1, 0, 1, 0 goes to 1/2, you can build it up and get to conclusions such as that. So what's the right answer? So the idea is, we want to say that we converge to something if we always get close to one specific value. If we get close and we stay close. The problem is, can we converge to 0? Well, do we always stay nearby 0? And the problem is no, because we sometimes jump in, but then we jump out. One term we're in, and the next term we're out. So we can't converge to 0. Well, maybe could we converge to 1? Well, no, same problem. Sometimes we're in, but then we're out. Then we're in, and then we're out. Can we converge to 1/2? No, we're never close to 1/2. And so this, we can say it diverges. Or you could say it does not converge. There's a couple of different ways you might phrase it. All right. Now some properties of limits. And these should be basically your intuition. And what are they? Well, suppose I know that my sequence A sub n goes to A, B sub n goes to B, then that says, what it's really saying is that A sub n is close to A. So I can think of A sub n as about A, and B sub n is close to B. So I think of it as like B sub n is about B. So I say, okay, well, what about A sub n plus B sub n? Well, it's about A plus B. And so that's the case. What if I scale A sub n? Well, this is about A, and if I scale it by K, I get about K times A. What if I multiply? So if the first term, A sub n, is about A, and B sub n is about B, if I multiply, what I get is about A times B. And division works too, as long as B is not 0. Now, if B is 0, things get interesting. If A is also 0, things get really interesting. And of course, if you go to 0 over 0, that means more work. More work. And yes, we will get to visit 0 over 0, by the way. What do we get to do with 0 over 0? Yeah, we get to bring back our terrible French accent. Oh, les hôpitaux. Oh, let us go get a baguette. Oh. Okay, so be ready. You might get to do that. In fact, we might even see that maybe today, maybe next time. The other thing that might happen is we say, well, look, we're having a hard time with our specific sequence, but I can bound my sequence, which might look unpleasant. And we're going to talk about getting rid of unpleasantries and saying, look, these parts are not important. These parts are. And try to understand, like, what parts are important. So if you can bound a sequence between two better behaved sequences such that these things both agree in their limits to L. So this says A is about L, the A sub n is about L, C sub n is about L. That's what this statement here says. So that's about L, which means that this thing in between them also has to be about the value for L. So it also converges to L. Now, the moral of this part right here is you should just think of the following, is that limits are intuitive. What should be reasonable will often work if you just think about breaking things into rules. Just be careful with your rules, and you'll be okay. All right, let's see. Okay, wow, there's so many good things to talk about. Okay. Well, we can have time for one more, I hope. All right, an example. A sub n is the square root of n squared plus 4n as we go from 1 to infinity. And b sub n is minus n as we go from 1 to infinity. What happens to a sub n plus b sub n? Well, let's just think about them individually. So I have the square root of n squared plus 4n, and n is getting big. So what happens to something that looks like the square root of n squared plus 4n for large values of n? Well, is it approaching anything, or is it just getting big? Is it getting small? What's happening to it? Okay, it approaches infinity, right? If you plug in a big value, you get out a big value. What happens to the b sub n? Net minus n. What is that going to do? Approaches negative infinity, right? Because n is getting big and b sub n. Okay, so what it seems to be that this is going to infinity minus infinity. All right. Well, what is infinity minus infinity? Do you remember what that equals? Infinity minus infinity equals more work. That is, yes, good. Woo! It's the correct answer. It's like, I didn't want to make this too easy. I want to work for my answers. Okay, well, let's think about what's going to happen. So you might say, well, hold on. If I have something, this infinitely big number, of course, nothing's infinitely big, but this really huge number, and I add this really huge other number that's negative, what can it be? Well, people want to think 0. Maybe it is 0. But the reason why we say infinity minus infinity requires more work is it's something which is called indeterminate. That means just from that expression, there's not enough information to determine what it is. It could be anything, and it also could be nothing. So we have to figure it out. So what do we really have? We have the limit as n goes to infinity of square root of n squared plus 4n minus n. Now, of course, for us to do more work, what's our favorite tool to use to do more work? Yeah, L'Hopital. Will we use it? I don't know. Maybe, maybe not. But if we were going to use it, what would we need? A fraction. So how do we make this into a fraction in a useful way? Well, among other things, we'd like to get rid of the square root. So, do we have something which can get rid of square roots? Squaring does get rid of square roots. I do agree with that. But I can't just arbitrarily square things, that even though it would be nice. And even on the exam last night, there were a lot of students who were like, oh, the square root of a plus b plus c. I'll just take the square root of a and the square root of b and the square root of c. And there were many tears shed that day. We can multiply by the conjugate. Okay. All right. The old tools are still the good tools, right? N squared plus 4n plus n, square root of n squared plus 4n plus n. And if we do that, this becomes the limit as n goes to infinity of, now the reason the conjugate works so well is it's n squared plus 4n. Then you subtract n squared because you square each term, and lo and behold, that gets rid of your square root. And downstairs you have square root of n squared plus 4n plus n. Now what happens upstairs? The n squareds cancel. Now I know at this point you're probably thinking, hey, I'm ready. L'Hopital this thing. Let's do it. But hold on. We don't have to L'Hopital everything. Not everything requires the French. Okay. Let's think about what we can do. Well, what's happening? Upstairs is doing what? It's going to infinity. Downstairs is doing what? Also going to infinity. Okay, so I know you're thinking, L'Hopital, Steve, L'Hopital. But let's do something else. It's called slowing it down. I would call it, in my generation, we would call it pump the brakes. So, this was something you would do on an old car. You don't do it anymore on new cars. But to slow something down, like if you're losing control, you're skidding on ice, you would pump the brakes to get control of the car. Here, we want to slow it down. So the question is, how fast is the top growing? What's causing the growth? Is it the 4 or is it the n that's making it big? Yeah, it's the n, because the 4 is always going to be 4. So we're going to multiply by 1 over n, which is the growth. So that's going to slow the top down. Now, how much does it slow it down? Just right. On the top, you get 4. Downstairs, well, the n times 1 over n makes a plus 1 here. And if you pass it inside the square, and I'm going to skip some of the details because we're kind of short on time, but it becomes n squared plus 4n over n squared when you pass it into the square root. And if you clean that up, lo and behold, you have 4 over the square root of 1 plus 4 over n plus 1. So we slowed it down. Now we ask the question, what happens as we go to infinity? What happens to the top? Yeah, it's 4. It's constant. What happens downstairs? Yeah, it's going to go to 2 because if 4 over n is 0, in the limit, it gets smaller and smaller. So we could even be really pedantic, right? Square root of 1 plus 1, meaning our answer is 2. And that's it. So let's go to the next example. Find the limit as n goes to infinity where an, where n goes from 0 to infinity, is given by this function, cosine n over n as n goes from 0 to infinity. Now, obviously, there's a really bad mistake here, because when n equals 0, this is undefined, because you can't divide by 0. Okay, we just fix it. All right, good. Now we can talk about it. Okay, so cosine n over n. Now you might say, well, what's happening to this? Now cosine, we're like, hey, cosine, that's pretty easy to understand. Because cosine does what? It just goes up and down and up and down. So that's what the cosine function is doing. All right, but what about cosine n when we're not looking for all values? See, this is like all values. But we're only looking for integer values. See, what happens is we're going to be 1, and then by the time we hit our next integer, well, that's cosine. Well, cosine of 0 is 1. Then what is cosine of 1? Well, it's something. It should be roughly right around here. And then cosine of 2, cosine 3. It's going to move sporadically up and down. So it's kind of hard to predict. You know, what is cosine of n? Cosine of n, it just bounces around. Not very easy to predict. But we say to ourselves, you know, fun fact, and we use this a lot, and that is that cosine of anything, doesn't really matter, n or whatever, is a bounded function, which means it's always between -1 and +1. Now, whenever we see cosine, essentially one way we can think of cosine is that, this is sort of like noise. Because noise, it's always sort of in there in the background. You might hear a little bit of static going on. But it never gets really too loud, never kind of goes completely away. It's just sort of always there. And that's what's happening with the cosine. It's just sort of always there. It's always moving up and down, but nothing really crazy happens with it. It stays bounded. And so really we should say bounded noise. Now the nice thing is when you know something is bounded, you can say, okay, what happens to the rest? Well, our conclusion is that cosine n over n is below 1 over n and bigger than or equal to -1 over n. Now, while this function can be hard to understand because this cosine of n, it's not so clear what's going on, each one of these two parts is fairly straightforward to understand. We already know that 1 over n goes to 0. So the negative of that would go to -0, but we still call that 0. So this is below something going to 0. It's above something going to 0. So what's the conclusion in the middle? Well, by the squeeze, we can say that this goes to 0 as well. All right. So there we go. It also goes to 0. All right. Well, let's do some more. Now, suppose we have following. All right. A little bit of a side note here. It says, suppose your function is differentiable. Then, if the limit of the function approaches L, then this f of n approaches L. So what's the difference between these two? Because this is like f of n. Now the difference between these two is the difference between continuous and discrete. Continuous says you're going to hit all values. So there's no gaps. Discrete says, well, we want to hit the whole numbers starting at some point. So you have to be careful. Now, the moral is, well, continuous things have more tools because we have le hôpital, le hôpital. That's a continuous tool. It involves derivatives. But sometimes discrete things can behave more nicely. So let's look at an example. Suppose we ask the question, what happens to f of x, which is sine of pi x? And a sub n is f of n. So we want to know, well, what's happening to this as we go off to infinity. Now, if you graph sine pi x, it's very similar to what was just graphed a few moments ago, but I'll graph it again. The only thing that the pi does is it sort of shrinks the period. And so we're going up and down. Now, if we ask ourselves the question, as we head off in this direction towards infinity, what is the function doing? Well, the answer is it's always going up and down and up and down. So the function itself doesn't approach a value. So what about this limit? So does that mean the limit doesn't exist? Well, now we have to be careful because it's a discrete thing going on here. Discrete is different. See, this says if a limit exists for the continuous case, the discrete case has to match it. But if the limit doesn't exist, all bets are off. Now the reason is, it all comes down to how you choose to sample. Now we kind of talked about sampling before when we talked about integration. We said, well, we're like sampling some of our data points and using that to get an estimate for what the behavior is in the long run. And now what's happening is we're sampling points on the function. So we're not taking every point on the function, we're taking points where our input is a whole number. So when you plug in 0, sine of 0 is 0. Okay, where's our next thing? Well, we're going to plug in 1. So that's sine of pi times 1, which is sine of pi, which is 0. How about 2? Well, sine of 2 pi, which is 0. 3 pi, which is 0. 4 pi, which is 0. In fact, we're always going to get 0. So it turns out that, yes, the way that this function is defined, it makes it look like it's something complicated going up and down, but our sampling is better. Our sampling is always going to hit the zeros. And so what's really happening is that our a sub n, which is sine of pi times n, is going to be 0. So the limit as n goes to infinity of a sub n, well, that's really the limit as n goes to infinity of 0. Now what happens to 0? Well, as n goes to infinity, it turns out that 0 will behave like 0. And so we get 0 out as our final answer. Now you might say, well, wait a second. What's different between this case versus the last case we talked about? And so the last case was this cosine. And the key was how you chose to sample. Because here we're sampling on every one. And so what ends up happening is that we kind of don't really fit in a nice pattern. Here, because we have that pi, it changes how frequently we go up and down, so that when we sample at really nice places. This is one of the dangers of sampling, is you might choose a bad place to sample, and you kind of somehow capture behavior that isn't really there. But of course, the downside is, if you don't sample, you can't capture everything. So what do? Well, oftentimes we sample a lot. All right, well, let's try another problem. Let g of x be the function x squared divided by e to the x. And a sub n is just g of n. So, what are we looking for? Well, we're really looking for the limit as n goes to infinity of n squared over e to the n. But here, the key here is we're thinking of n as a whole number. Now, you might say, well, let's use the L'Hopital. And the answer is, well, we're kind of going to do that. Absolutely, that's the direction we're going. Technically, we can't do it here, because it comes back to our discrete versus continuous. But we say, look, let's look at the continuous case. And if in the continuous case it works, then we're fine. So let's just follow through and see what the continuous case says. So let's look at the limit as x goes to infinity of x squared over e to the x. Well, this is going to infinity, big number upstairs, and infinity, big number downstairs, which, as we all know, means more work. More work, absolutely. Okay, well, what do we mean by more work? Well, this is an indeterminate form, which means we turn to our good friend, L'Hopital. Oh, L'Hopital, put down your baguette. It is time for us to do more math. And we say, okay, all right. So, what do we do? L'Hopital it. Well, we're going to get the limit as x goes to infinity. And remember, it means take the dirt to the top, divide by dirt to the bottom. All right. Well, that's going to infinity over infinity. Well, which means, again, L'Hopital. Oh, L'Hopital, put down your croissant. We must work again. All right, so we do it again. And we will keep doing it, hopefully until we figure out what's going on. So now we get 2 over e to the x. And now we're fine. See, the upstairs goes to 2. Game over. Game over. Why? Well, so what's happening is we're going to 2. It's not 0, not infinity, it's a number, which means that whatever's going to happen, it's going to happen now. So it's 2 over a big number. Well, if you take 2 over a big number, it's a small number. And as that number gets bigger and bigger, your result gets smaller and smaller, so you get 0. So this point, you're probably thinking, wow, all sequences go to 0. Well, no, but it's a good place to start, right? We start with the easy ones, and then we'll work our way up to the harder ones. It's better than working and starting with the harder ones, and then working our way down to the easy ones. All right. So let's talk about a couple of basic sequences, things that we might be seeing. So here's a few things that you should know. These are going to be very useful. First off, if I have the nth root of n, that goes to 1 as n goes to infinity. If I have a power of x raised to the nth power, and if that x is small, so between -1 and +1, then if I multiply it by itself many, many times, eventually I'll get to 0. Now if it's big, it's going to blow up. And of course, and if it's exactly 1, it does boring stuff. If I have 1 plus x over n, and I raise it to the nth power, that's e to the x. For any x you choose, that's always going to be true. And if I take the limit as n goes to infinity of x to the n divided by n, oh wait, no, that's not n, it's something else. It's a n factorial. Okay, we should talk about that. Factorial, what does that mean? Well, just a refresher, we probably have seen this before. N factorial means you start with n, then you multiply it by the next number down, n minus 1, then the next number down, and then so forth and so on, all the way until you get to 1, and then you stop. Well, you don't want to go any further. If you multiply it by 0, it would be 0. Now, factorials go pretty fast. You know, you might think, not originally, not initially, 0 factorial by convention is 1. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. And you're probably thinking, that's not so fast. Well, by the time you hit 8 factorial, that's 40,320. That's 8. And it gets bigger and bigger. Now, why is it true that regardless of what choice of x you pick, x to the n divided by n factorial is going to get small? Well, there's one way to think about it which can help. We're going to go through and do this a little bit more later on. We can't do L'Hopital here because we don't really have a good function that is in our class that behaves like factorial. Now, there is a function, it's called gamma, that does behave like factorial, but we don't know it. But instead what we can think about is what happens if we were to go one more step? Well, the answer is on the top you multiply by x. And on the bottom you multiply by n, right? Because look at what you have. If you look at this factorial here, you have n plus a whole bunch of stuff, which is really n minus 1 factorial. So, on the top you multiply it by x, and on the bottom you multiply by n. But remember, x is fixed, because it's not changing. The thing that's changing is n. So, if x is 1,000,000, then initially it looks like the top is better, because you're multiplying by something bigger on the top than on the bottom. But that's eventually what's going to happen. N will catch up. By the time n is 1,000,000, you're multiplying by 1,000,000 on the top and 1,000,000 on the bottom. And then every time after that, what you multiply by is something a little bit smaller than 1. Because the top is x and the bottom is bigger than the size of x. And so that's what's happening, is that the bottom dominates. In fact, factorials grow very, very quickly. So we got to be a little bit cautious about them. Well, let's pick one of these two. Let's see which one is probably easier. Let's do this one. I think this one's a more interesting answer, because I think it's good to refresh our memories about how this works. I think we might see things like this again. So what do we have? We want to look at the limit as n goes to infinity of 1 plus x over n raised to the nth power. Now, currently, this inside part goes to 0. So you have 1 raised to a huge number. So it's like 1 to the infinity. Now, how do we treat 1 to the infinity? Well, the answer, it's not 1. It's not infinity. It's more work. This is an example of an indeterminate form. Now, can we do L'Hopital? No, we cannot. Because the problem is, it's not a fraction. To do L'Hopital, we need a fraction. So, we need a new plan. Our new plan is, let's figure out a way to rewrite this in a way that we could do L'Hopital. So, let's call whatever our limit is, we'll call it L. So we'll look at log of L. Now, why the log? Well, the problem is I have something changing in the base and the exponent. So I want to bring the exponent down. So the way to bring exponents down is to use logs. The other nice thing about logs is they work well with limits. So I can pass the log through. So this is log of 1 plus x over n to the nth power. And now, what's going to happen here is that n up in the exponent, well, that is going to move down. And in fact, not only are we going to move it down, we're going to move it all the way down. So it goes into the denominator. So what is that going to give us? Well, that becomes a limit as n goes to infinity. Upstairs, natural log of 1 plus x over n. And now, it comes down as an n, and when I move it downstairs, it's a 1 over n. Now what's going to happen here is the top is going to go to log of 1, which is 0, and the bottom is going to 0. So we call upon our friend one more time. Oh, L'Hopital! Let us put down the poisson, the fish, and let us go do some work. And so we take L'Hopital, use that, because it's going to 0 over 0. So we have a limit as n goes to infinity, and the root of the top is 1 over the inside times the root of the inside. Well, the root of the inside with respect to n, would be minus x over n squared. And here I'm thinking of n as being a continuous thing, not as a discrete thing, because if it's continuous and the limit exists, then we can pretend like it's discrete. The derivative of 1 over n is minus 1 over n squared. And lo and behold, we see nice things happen because we've lived a good life. So nice things should happen. The n squareds cancel. The minuses cancel. And now what happens? Well, downstairs there's nothing left. So what happens upstairs? Well, you have an x, all right. There's a 1. And then you have 1 plus x over a huge number. That makes it 0. That's just 1. So that means our limit is x. Wait. Not quite. Go back. The log of our limit is x. So, if the log of our limit is x, and our limit, to get rid of the log, we use the exponential function, is e to the x. And that's how we get that result. Similar process, you can prove that the nth root of n goes to 1. All right, good. Well, another thing that we'll oftentimes see, and you might see this, for instance, depending upon how you do differential equations, you see things called recursive sequences. And recursive sequences says, let me figure out what I am based on what's come before. So, you're looking at the past to tell you what to do now. Here's a very simple example. So, a0 equals 1, and to get the next term, a sub n, that's n times a sub n minus 1. So we want to find a simple expression. Well, let's just follow the pattern. a0 equals 1. What about a1? So we follow the rule. So that's n equals 1. So I'm thinking n equals 1. So that's 1 times a0. a2 would be, okay, that's n equals 2. 2 times a1. And a3, 3 times a2, because I'm putting n equals 3. Everywhere I see n, I put 3. And so forth and so on. Now, at this point, you're probably like, I don't see any pattern. Well, that's because we're not doing the right thing. We also need to replace what a0 is. Well, a0 is 1, so I'll do it 1 times 1, which I'll leave as 1. Now I say, a1 is also 1, so 2 times 1. So you're saying 2. Well, yeah, let's go ahead and leave it as 2 times 1. See, sometimes you get this mindset, I should always simplify. But when you're looking for patterns, simplification is a dangerous thing to do. Simplification can lead you astray. So you want to be a little bit careful. So next one, 3 times 2 times 1. Next one, 4 times 3 times 2 times 1. Seems familiar. a5, that's 5 times a4. That's 5 times 4 times 3 times 2 times 1. Do you spot the pattern? Do you see what it's doing? If I'm a5, I just multiply the first 5 numbers together. Which means if I'm a10, that looks like it's going to be multiplied the first 10 numbers together. Well, we have something that corresponds to multiplying the first so many numbers together. It's actually what we talked about before. So that's 10 factorial. And in general, we can say, aha, this is a way to find n factorial. So that's a recursive way to describe n factorial. Okay, a couple more. There's some famous examples of this. So, let b0 equals 0, b1 equals 1, and then bn is the sum of the previous two. Well, what does that mean? Well, let's just say that we'll write the pattern down. 0, comma, 1. Now for the next term, it says go back and add the previous two together. So 0 and 1 makes 1. All right? Next, 1 and 1 makes 2. 1 and 2, 3. 2 and 3, 5. 3 and 5, 8. 5 and 8, 13. How many are we up to? 1, 2, 3, 4, 5, 6. I think we need one more, right? This is B0, 1, 2, 3, 4, 5, 6, 7. Yep, one more. Next one, do you see it? 21. 8 plus 13. Now, you might recognize these numbers. In fact, they're not so hard to write some terms down. 34, 55, 89, and 144, so forth and so on. You've seen these before, and these are famous, or maybe, better yet, infamous. These are called the Fibonacci numbers. Now, who was Fibonacci? Well, that's actually not the person's name. He was called Leonardo da Pisa, also known as Fibonacci. And what did he do? He wrote the very first algebra book in sort of Latin. And it was a way for people to learn how to do things like add numbers and manipulate terms and subtract and multiply. You're probably thinking, that doesn't sound so complicated. Well, back in his time, people used Roman numerals, which is terrible if you want to do anything. They used to have to go hire a mathematician to say, hey, mathematician, what happens if I want to, have so many of this plus so many of that? And the mathematician would add for them because they couldn't do it themselves. And he said, no. Look, anybody can do it if you have the right system, which is the Arabic numeral system. So he was the one who got that going. And it just changed the world. A little bit of math goes an amazingly long way. Of course, now these numbers are sort of too famous. And so if you watch, for example, the Da Vinci Code, well, these numbers show up. Why? Well, not because they're special, but just because they're kind of famous. They're not actually all that potent. There's lots of other sequences that are more interesting. All right, our last example. Let C0 equals 0, and Cn is n plus Cn minus 1. It's a little bit different. See, we did n times a few minutes ago, n plus. So what do we have? C0 equals 0. C1 would be 1 plus C0. So 1 plus 0. Okay. C2 would be, I'll go ahead and write that down. So I'll just write that as 1. 2 plus C1, which is 2 plus 1. C3 would be 3 plus C2, which is 3 plus 2 plus 1. C4, 4 plus C3, so that's 4 plus 3 plus 2 plus 1. And it looks like, we're instead of multiplying, we're adding. So in general, we can say the nth term, which is n plus Cn minus 1, would be the result if you added all of these together. They're probably thinking, well, n factorial, that was the notation when we multiplied, so maybe there's like an n upside down factorial sign if we're adding, and no, there's nothing like that. Now these numbers are also famous, and they have a name. They're called the triangular numbers. Now you might say, why do we call them the triangular numbers? Well, let's look. Let's count our dots. How many dots are there? Well, that's an easy one. There's 1. Now how many are there? Well, there's 1 plus 2. And then 1 plus 2 plus 3. And then 1 plus 2 plus 3 plus 4. 1 plus 2 plus 3 plus 4 plus 5. And so forth and so on. So what happens is every time we add a row, the number of dots in that row is 1 more than in the previous row. And if you look, this looks a little bit like a big triangle because it's a big triangle. So the reason we call it the triangular numbers is we're counting dots. All right, well, so that's good, but it doesn't get us to the challenge. How do we find a simple expression? Well, let's do a simple case. And let's see if we can't convince ourselves that's not so bad. So we have some dots. We want to know how many dots there are. What I'm going to do is I'm going to come to the bottom row, and I'm going to put 1 dot. Then in the next row, I'll put 2 dots. And in the row above it, I'll put 3 dots. And then I'll put, this won't surprise you, 4 dots. And then I'll put 5 dots. You're probably thinking, whoa, that's a lot of dots. But look at what we've done. If you look at this picture, what we have is we really have 2 triangles. All right. Well, that's not so surprising. But there's more than that. It's not just that we have 2 triangles. We put them together, we were like, ooh, it's a parallelogram. But now, let's do a count. First off, how many rows do you have? You have 1, 2, 3, 4, 5. So 5 rows. In general, the number of rows, if we started, we'll call that n. Okay, how many dots per row? All right, well, let's see. Here there's 1, and then there's plus 5. 2 plus 4. 3 and 3. 4, 2, 5, 1. So what's going to happen is it's always the same number of dots per row. And that number is going to be n plus 1. Okay, so you now know the number of rows. You now know the number of dots per rows. So we have that the number of dots has to equal n times n plus 1. All right. Now the question is, that's not what we're after. How do we get to what we're after? Well, the number of dots, is n times n plus 1, is if we put 2 of these together. So what's our final answer? Our final answer is that we can say that the nth triangular number is half of that. So in particular, we can say it is n times n plus 1 over 2. Let's check this. So let's see. Here we go. C4, that should be 4 plus 3 plus 2 plus 1. That's 10. Well, let's take, is that equal to 4 times 4 plus 1 is 5 over 2. Well, that's 20 over 2 is, yes, it works. Wow, that's so cool. That's so cool. Yeah, that's a beautiful idea. Now we're not going to use this too much, but it's good to get in the habit of it because these kinds of tools, these recursive tools, become really important in certain settings. Again, depending upon how you do differential equations, this is a very powerful technique to use. And learning to use sequences is going to be our foundation. Because, at the end of the day, what we're trying to say, what happens as we go off to infinity? So we want to make sure we have a good grasp. Now, some parting words of advice. If what you've seen today makes you very nervous, I want you to relax. It's okay. We're going to do limits. We definitely will do limits, but we're not going to get down into the very fine details. Focus on the intuition. And if you can get through the intuition, you'll be okay. We're just going to focus and make sure we understand the principles. Now, where are we going next? Well, now that we know the dot, 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 how do we describe this long infinite list of numbers? Now we're going to start adding them up. So starting next time, we're going to get a little bit more series. All right, that's it for today. Okay, see you next time. Bye.